Safe water at the turn of the tap. In the modern era, it's hard to think that something we so often take for granted could be so deadly. But you only need to look back a few generations to see widespread illness and death from waterborne diseases like cholera and typhoid. These bacteria live in the gastrointestinal tract of sick humans, and wastewater that is connected to water supplies provides a nearly perfect vehicle for the spread of disease. Over time, a number of additional pathogens have been identified in water supplies. Yet thanks to modern water and wastewater treatment, waterborne disease outbreaks in North America are nearly unheard of today. The use of chlorine to disinfect public water supplies is credited as one of the top public health advancements of the 20th century, and has been responsible for the near elimination of cholera and typhoid in the developed world. Globally, the effort to combat waterborne illness continues, with chlorine as the frontline weapon in preventing the spread of illness and deaths from these pathogens. Chlorine has been used for large-scale disinfection of public water supplies for more than a century. It was not readily accepted at first, and it took many years to understand how to control its use. Consistent chemical supplies, metering, and monitoring equipment are now more consistent and allow for more precise application, allowing water operators to meet higher expectations and more stringent regulations. The primary goal of water treatment regulations is to protect public health, and waterborne pathogens are one major focus. In the U.S., the Safe Drinking Water Act regulates the disinfection of public water supplies. AWWA regulations, including the Total Coliform Rule, the Surface Water Treatment Rule, and the Groundwater Rule, specifically address microbial protection. Following the discovery of trihalomethanes, or THMs, in the 1970s, disinfection strategies became more complicated. Newer rules set specific limits on disinfection byproducts, or DBPs, and cap allowable residual disinfectant levels. In the U.S., regulations place high demands on water system operators. No longer are they simply dosing water with a preset feed rate. A careful balance must be struck to achieve simultaneous compliance, adjusting treatment strategies and disinfectant application to meet the demands of specific, and often changing, water supplies. In modern water treatment processes, chlorine has several uses. It is often used as a primary disinfectant, where a larger dose is applied for a sufficient contact time to destroy or inactivate pathogens. It is also used as a secondary disinfectant, the main preservative for drinking water added as a final step before water leaves the treatment plant to control biological regrowth in the distribution system. In addition to disinfection, chlorine is also useful in controlling algae growth within the treatment plant, oxidizing iron and manganese, and taste and odor control. It can also improve the coagulation process for particle removal. However, the use of chlorine contributes a distinct odor that consumers may complain about. Free residual chlorine reacts with naturally occurring organics such as humic acids and bromide, producing disinfection byproducts with health concerns, not all of which have yet been regulated. Trihalomethanes and haloacetic acids are regulated such that chlorination must be controlled so as not to produce levels that are too high. As such, water treatment operators and engineers must understand how chlorine disinfection works, how to monitor and control the application of chlorine, and how to maintain a sufficient but not excessive chlorine residual. Chlorine is effective, economical, and readily available. It remains the most common disinfectant in North America. It is a strong oxidizing agent and reacts with various types of organic substances, metals, and ammonia. Chlorine dissolves in water to produce hypochlorous acid, which is a strong disinfectant. The hypochlorous acid then dissociates, in part, into hypochlorite ion, a weaker disinfectant. There are several ways in which chlorine works to disinfect water. Regardless of the specific mechanism, chlorine inactivates pathogens and renders water safe for drinking. But chlorine does not render water sterile or free of microorganisms. Safe drinking water can still contain thousands of microorganism cells and spores. For this reason, chlorine is typically used as the secondary disinfectant or preservative in treated water that is sent out to every home and business, making sure microorganisms remain under control. Because it is so reactive, chlorine gas is not naturally found and must be generated. Chlorine is commonly used in disinfectants such as bleach and is widely used in industrial processes and the production of plastics. For water treatment, several forms of chlorine are typically used. Chlorine gas is the most common form used for drinking water disinfection. It is generated through the electrolysis of sodium chloride dissolved in water. This produces chlorine, hydrogen, and sodium hydroxide. Chlorine has a boiling point of -34.6 degrees Celsius and is a gas at room temperature. However, it is typically compressed into a liquid for easier transportation and storage. It is shipped and stored in pressure vessels as a liquefied gas under pressure. The containers have both liquid at the bottom and gaseous at the top chlorine inside. Utilities generally use 1-ton containers, although quantities ranging from 150-pound cylinders to 90-ton railcars are available. Chlorine gas is removed from a cylinder or ton container by a vacuum-operated gas feed chlorinator, which produces a vacuum with a water-operated venturi. This mixes the chlorine gas with water and produces a high-strength chlorine solution, which is piped to the injection location in the treatment plant and mixed into the water. For very large applications, the liquid chlorine at the bottom of the container can be withdrawn and converted to a gas using an evaporator. The resulting gas is then fed using a chlorinator. Pure chlorine is a dangerous chemical and must be carefully monitored and secured. As a result, other safer forms of chlorine have been developed. Alternatives to gaseous chlorine are hypochlorites. Calcium hypochlorite, known as high-test hypochlorite, or HTH, contains up to 70% available chlorine. It can be supplied in granular and tablet form, which need to be dissolved in water and is generally used for disinfection of new and repaired water mains, storage tanks, and smaller water volumes such as swimming pools. It's also useful for small water systems where continuous monitoring of chlorine feed is not available. Sodium hypochlorite is more commonly used in water treatment. It's a clear, light yellow liquid and in industrial strength contains up to 20% available chlorine. 12% is a common strength used by utilities. By comparison, household bleach contains about 5% available chlorine. Over time, sodium hypochlorite decomposes and forms undesirable chloride ions in finished water. Solutions at higher strengths can lose 2 to 4% of available chlorine per month at room temperature. Storage is not recommended for longer than 15 to 25 days. Lower strength solutions do not degrade as fast, so some utilities dilute a stock 12% hypochlorite with water to create a 6% solution for stability and to minimize chlorate formation. Sometimes regulatory requirements result in the need to store large volumes of disinfectant on site. This is a consideration that must be factored into decisions concerning disinfectant selection and use. As a solution, sodium hypochlorite is fed using a metering pump, a chemical feed pump with variable speed to adjust the dosage. Calcium hypochlorite requires a mixing tank, and sometimes a day tank, to create a solution from dry stock to feed the metering pump. While hypochlorites are chemically distinct from elemental chlorine, once added to water, they also form hypochlorous acid and hypochlorite ion. Another form of chlorine used by water utilities is chloramine. Chloramine is sometimes produced naturally during treatment through the reaction between chlorine and ammonia present in source water. It is important to know if source water contains ammonia. More often, utilities intentionally introduce ammonia to react with chlorine and create chloramine as a disinfectant. Chloramine is a weaker disinfectant, but is attractive as an alternative secondary disinfectant as it creates less chlorination byproducts. It is produced on site by adding chlorine and ammonia to the water in correct proportions. A typical pH value and a chlorine to ammonia ratio between 4 and 5 produces monochloramine, the preferred form of chloramine. If pH drops, or if the ratio of the two chemicals is not correct, dichloramine and eventually trichloramine can form. These two compounds are undesirable. They are ineffective disinfectants and impart an unpleasant odor to the water. As more chlorine is added relative to ammonia, monochloramine changes to dichloramine, which changes to trichloramine, then nitrogen and chlorides, and then finally, free chlorine. Monochloramine requires much higher concentrations and much longer contact times to get the same oxidation and disinfection effects as chlorine. It is a weaker oxidant and has a less noticeable odor. However, monochloramine creates a long-lasting residual. Because of its persistence, it is often used as a secondary disinfectant for preserving treated water in the distribution system. Utilities create chloramine in one of three ways: by feeding ammonia to the water, followed by chlorine, by treating the water with chlorine and adding ammonia at the end of treatment, and preforming chloramine before feeding it to water. Some complex chemistry can happen in water treatment. However, the basics of chlorine disinfection can be understood by learning some simple chemistry and terminology. One of the fundamental concepts of water disinfection is the CT value, the concentration of the disinfectant multiplied by contact time with the water. The CT value is a measure of how much disinfection is needed to inactivate many waterborne pathogens. Studies have determined CT goals for disinfection. To reach these goals, the concentration of chlorine can be increased or the contact time with the water can be lengthened. CT values account for the pathogens of interest, the type of disinfectants used, water temperature, and pH. Chlorine demand is the amount of chlorine used up in reactions with material in the water. Generally, demand is met during the first few minutes. It is the difference between the initial dose and the measurement of residual chlorine at the end of the contact time. If a 5 mg per liter dose is applied, and the residual after 30 minutes is measured at 2 mg per liter, the chlorine demand of the water is 3 mg per liter. Chlorine demand is directly affected by source water quality, including the amounts and types of organic and inorganic material present, and the effectiveness of pretreatment techniques. For example, well-optimized coagulation, flocculation, and sedimentation processes can lower chlorine demand by removing some of the organic material prior to primary disinfection. Because chlorine reacts with organic matter to form disinfection byproducts, holding back on chlorination will reduce DBP production during disinfection. When chlorine gas is added to water, hypochlorous acid is formed. Hypochlorous acid dissociates in water, forming a hypochlorite ion and a hydrogen ion. The combination of hypochlorous acid and hypochlorite ion are known as free chlorine residual, or free available chlorine. This is the reactive chlorine available for oxidation and disinfection. This basic chemistry is the start of the disinfection process. As other chemical compounds and organic matter in the water react with the chlorine, additional, more complex reactions occur. Generally, chlorine is doing these three things. It is oxidizing iron, manganese, and other matter. It is disinfecting the water, and it's satisfying the water's chlorine demand so that a stable water can be provided for the distribution system. To properly monitor and control the disinfection process, operators must understand how chlorine is measured in water and what those measurements include. Chlorine measurements are one of the most important tests performed by operators. The most common test is the DPD color test, where a reagent is added to a water sample and the resulting color intensity is measured to determine chlorine levels. Portable and benchtop equipment is available for DPD testing. Online monitors can also be used. Another common test is called empirometric titration. It is more precise and capable of determining many chlorine species that may be present. Empirometric titration is generally performed in the lab, although online monitors are also available. Both tests can measure either free or total chlorine. It's important for operators to know what they are measuring and understand the difference between the two. Total chlorine is the chlorine concentration after the chlorine demand is satisfied. It is a measurement of both combined chlorine and free chlorine. Free chlorine is the measurement of chlorine as chlorine gas, hypochlorous acid, and hypochlorite ion. When chlorine reacts with organic nitrogen and ammonia, free chlorine is converted into combined chlorine. For water treatment, this is generally a measurement of chloramines. For example, an initial chlorine dose is added to source water. To satisfy the chlorine demand, some of this chlorine reacts with materials in the water to form non-reactive substances and can no longer be measured in chlorine tests. The remaining chlorine is measured as total chlorine. Part of the total chlorine has been used up in reactions with ammonia. It is still measurable as chlorine, but no longer available for disinfection. The remaining chlorine available for disinfection is called free chlorine. Free chlorine will always be less than total chlorine. As with any process measurement, the results are only accurate if the testing equipment is properly calibrated, maintained, and operated, and only meaningful if the operator understands how the measurements apply to the process they are controlling. One challenge operators face is that the analytical method for total chlorine can't distinguish between the various forms of chlorine, particularly when trying to account for chloramines, or combined chlorine. When working with chloramines, there is a point in disinfection where more chlorine is added, yet the measurement for total chlorine drops. This can be confusing and is best understood by learning how breakpoint chlorination works. In this illustration, chlorine dosage is shown on the horizontal axis, and measured total chlorine residual is shown on the vertical axis. The straight 45-degree line illustrates a zero-demand water, a hypothetical case where there is no material in the water to react with chlorine, and chlorine residual matches chlorine dose. This is rarely the case. In breakpoint chlorination, as the chlorine is introduced, there will initially be no residual measurement as the chlorine demand is satisfied. The residual will then start to rise. Again, there is some complex chemistry happening along the breakpoint curve, but basically, chlorine is reacting with substances in water in several stages. First are reducing agents, including iron, manganese, hydrogen sulfide, nitrites, and thiosulfates. These are oxidized by chlorine, neutralizing color, tastes, and odors. None of these non-reactive materials are measured in the chlorine residual test. Chlorine also reacts with ammonia in source water to form monochloramine. Chloramines and organochloramine compounds together are measured as combined residual chlorine and will factor in the total chlorine residual measurement. This test can't distinguish free from combined chlorine. It measures all forms of chlorine. Free chlorine will always combine with ammonia at a 5:1 chlorine to ammonia ratio. For a fixed amount of ammonia in the water, as more chlorine is added, the monochloramine residual will increase until the 5:1 ratio is reached. This is the peak on the chart. To the left of this point, there is free, uncombined ammonia in the water. To the right of this point, there is no more free ammonia left to combine with the chlorine. At this point, additional free chlorine starts to convert monochloramine to dichloramine, and total chlorine residual decreases even though chlorine continues to be added. Further addition of chlorine forms dichloramine and trichloramine, then further reacts with chloramines and chloroorganic compounds into end products including nitrogen gas, nitrous oxide, hydrochloric acid, and nitrogen trichloride. This step further reduces residual chlorine. Once oxidation is complete, the breakpoint has been reached and the total chlorine measurement begins to increase again. At this point, all chlorine is free, not combined. This residual is known as free residual chlorine, or the breakpoint residual. As the continued addition of chlorine corresponds to a rise in free residual, it indicates that there is little left to react with the disinfectant and that oxidation has occurred. The achievement of breakpoint means that the immediate chlorine demand has been met. The finished water should be stable for maintaining a chlorine residual in the distribution system. In the treatment process, operators look for the chlorine breakpoint and the stabilized rise of free chlorine residual as a sign that sufficient chlorine has been added to establish a free chlorine residual. In disinfection with combined chlorine, operators look for the peak and carefully add the correct amount of ammonia to maximize formation of monochloramine and avoid formation of free chlorine. In addition to organic and inorganic materials in source water, which react with chlorine, there are several factors which affect chlorination and the effectiveness of disinfection. First is pH. In the basic reaction of chlorine and water, a combination of hypochlorous acid and hypochlorite ion is formed. As pH rises, more of the free chlorine is in the form of hypochlorite ion. Hypochlorous acid is a stronger disinfectant and is more highly reactive than hypochlorite ion. As a result, effectiveness of chlorine starts to decline above a pH of 7.5. In general, the higher the pH, the greater free residual chlorine will be required. For a given level of disinfection, the CT value at a low pH is less than the CT value at a high pH. CT values for monochloramine are not pH dependent. Lower pH conditions result in better disinfection and lower concentration of some chlorinated DBPs like THMs. However, in some waters, lower pHs can lead to higher formation of other chlorinated DBPs, such as haloacetic acids. The effectiveness of chlorine also varies directly with water temperature. Chemical reaction rates are typically faster at higher temperatures. The higher the temperature, the less contact time is required, as disinfection occurs more quickly, but DBP formation must be more closely watched. In addition to regulated disinfection byproducts, products of chlorination can cause aesthetic and health concerns. For example, some cyanobacteria can release toxins and odor compounds when their cells are lysed open during chlorination. The EPA has issued health advisories on cyanotoxins that states may regulate, and it's desirable in some situations to physically remove algae and organic matter before treating water with chlorine. Interference substances must also be considered. Chlorine is only effective if it contacts the microorganisms it is meant to inactivate. Turbidity, caused by tiny particles of minerals or organic matter, can shield pathogens from disinfection. Consider that pathogenic viruses occur in water because of human and animal fecal waste. These viruses are therefore associated with the waste matter and can be protected to some degree. The reduction of turbidity during treatment reduces pathogens. Chlorine can be applied both before and after the treatment process. Each has specific goals and considerations. Pre-chlorination is a common practice where chlorine is applied to raw water before other treatment processes. It helps in the coagulation and removal of tastes and odors, and kills bacteria, algae, and microorganisms which settle out in sedimentation. Pre-chlorination also aids in meeting the chlorine demand and achieving breakpoint, although it may not count towards disinfection credit, depending on the state. Post-chlorination is the addition of chlorine at the end of the treatment process. It is used for proper disinfection to achieve required CT values and helps ensure proper residual as the water is sent into the distribution system. In certain situations, it may be desirable to eliminate pre-chlorination to control the competing demands of water treatment. This means other treatment processes must reduce organic compounds, interference substances, and DBP precursors prior to chlorination, reducing chlorine demand and DBP formation. Elimination of chlorination prior to the filters promotes biologically active filters, which in some situations can effectively remove DBP precursors and produce more biologically stable water. Utilities can also use alternative oxidants to better control disinfection byproduct formation, as well as other challenges. For example, chlorine dioxide, ozone, or potassium permanganate can be used for oxidative pretreatment, and chloramines can be used to provide a disinfectant residual in the distribution system. Such alternatives must be carefully studied, however, since each has its own set of issues and byproducts. In the US, treated surface water is required to have a disinfectant residual as the water leaves the treatment plant, and utilities must monitor the water throughout the distribution system to ensure that minimum residuals are maintained. This is drinking water's key preservative. However, higher free chlorine residuals contribute to increased DBP formation, and many customers, particularly in the food and beverage and healthcare industries, are generally averse to higher chlorine levels in their drinking water. Again, a strategic balance must be maintained between minimum effective doses and maximum allowable levels. A chlorine or chloramine residual in the distribution system deters the growth of microorganisms and helps to address intrusion. It can also provide early warning. A sudden loss of chlorine residual may indicate contamination. It is something consumers expect in their water, therefore being easier to communicate about and serves as one quick indicator of changes that need attention. Potable water is perishable. The residual does not last indefinitely. Chlorine or chloramine in water dies off over time, depending on many factors such as water temperature, corrosion byproducts, and organic matter. This is called chlorine decay. Depending on the amount of material in the water, the chlorine decay rate might be a few days or weeks. The decay rate for chlorine is faster than for monochloramine. It may be necessary to provide secondary or booster chlorination or chloramination at points in the distribution system where high water age, corroding old mains, or other issues exist. Similarly, it may be necessary to flush certain areas regularly to bring in fresh water with a higher residual. Chlorine has long been the cornerstone of water disinfection and a critical tool in safeguarding public health. It is relatively easy to acquire and use, and feed systems and measurement controls are readily available. But chlorine is not the silver bullet for water treatment. It is just one of the multiple barriers for ensuring safe drinking water. Regulations and disinfection byproduct concerns have made the application of chlorine and other disinfectants more challenging, but the benefits have long been shown to outweigh the risks when properly applied. A skilled and knowledgeable operator who understands disinfection strategies and the proper use of chlorine is a vital component of meeting the challenge of providing safe water while minimizing undesirable byproducts.